So here we go for the Jupyter Notebook on regression part 2. Again, this is a very small data set with 60 houses from 3 neighborhoods. So in each neighborhood only 20. Why? Because when you look at a certain, say, 4 month period, in each of these neighborhoods, there's only a few houses sold. So even though you may have the whole of America data set, the most important for predicting new sales in those neighborhoods is probably the houses which have been sold in those neighborhoods within a couple months. So a part of this problem is really to predict based on very few data. And to some extent, probably the full data set of millions of American houses is probably going to affect a little bit this thing, but more like an index. Probably if you have the general, uh, you know, housing market index, that's already enough, and you don't need the specifics. So also it's good for you to learn first with a small data set for several reasons. Okay, so here first, uh, import all what we need as usual. Python basic, we saw it in the last video. NumPy, we saw it in the last video. So getting the data into uh, the Panda data frame. So here data, now data is PD stands for Panda, read CSV, and here I have the Zillow cleaned up train CSV. You need this file in your working directory, and now it's read into our Panda data frames called data. Again, I repeat, what I do most, I analyze data often because I do algorithms and so on, so I spend thousands of hours in my life with data. And most of the time, I just, first thing I want to need the shape. So here I have 54 houses and 12 features. Then the next most important is the type. What is it? And this is a data frame. Okay. Then you have these Panda data frame head. It just shows you the first 4 lines, and it's always good to see more or less what it looks like. So you see here the selling price is what we want to predict. Zip code, that is a date. Um, they were all in a relatively short period of time. I didn't use that for my prediction. You could use it actually because some are a little bit later and some a little bit earlier. And we put the date in decimal because for some regression purposes or so it might be useful. So 2012.1 is a tenth of a year. 2014 and the tenth for a year, so a month and 2 weeks or something. Anyhow, so you also have last sold price, last sold date. That is when it was sold before this selling price, which we have here. So here, this column is selling price, and then we have last sold price, last sold date, and the Zillow estimate is given here. Of course, you don't want to use a Zillow estimate, but it's all about seeing if you can beat the Zillow estimate. So you can see what is a prediction error between, say, the selling price and the Zillow estimate, and then you can build your own prediction and compare. As already mentioned, Panda data frame to subset, so to get only the first 9 rows and the first 3 columns, is you need this iloc method. So here we go. And that's a little bit bad because if it is a NumPy matrix or array, you don't need this thing. You can just do data and then leave the whole thing out. But what you want. Another important thing is I always want to see what are the columns. I use this all the time. What are the columns? Then here again, set. So data zip code would just give me the column with all the zip codes. Let's quickly see. And now I want to know what, here's small data, but I want to know what zip codes do I actually have. So I do set, and in a set you cannot have 2 times the same element, so it will list each element only once. So I see I have 3 zip codes. Now I want to see what are the house types, and I have single family, and then a blank space. So I need to correct this. How do I do that? I do data house type, and now wherever this is equal to, I put two equals, is logical equal, is not loading into a variable some information. Wherever it is single family blank space, that's a mistake. It should be single family without that blank space. So I go data house type, and then I restrict to those where they are single family written wrong, and I make it single family written correctly. Now with this I'm going to replace the house type single family blank space, which is obviously a spelling mistake. Here we go. Let me double think. Yes, it's correct. Hop. And now let's see again. You see single family now is written correctly. So if you want to see your data set, that's why I like, for somebody who start with a small data set. You see a lot. See single family. Okay, there's no more. There you can see the full data set to see that nothing wrong has happened. Hop. Here we go. Great. Okay. Let me clear the output. You go on cell, cell type, all output, clear for that cell. I hope I didn't clear the others. Okay. Oh, did it? So, I cleaned all the outputs. Anyhow, let's quickly see. Okay. Now, we want to analyze and display with matplotlib. So let me run this. See, here we create the vector column, but we have not one equal, but equal. That's a logical equivalent. So wherever data zip code is 30309, we get a true. So this thing, data zip code equals, that is equivalent to 30309, gives me a logical vector with false and true where it belongs to that zip code. And now I can, for example, subset my data selling price to see in that neighborhood of 30309 what are the selling prices. So you see here, when I do data selling price, that gives me only the selling price, not all the columns of my data set, of my data frame, but restricted to where the zip code is 30309, and I see here those selling prices. We can calculate the mean, for example, just for that. I added with the method mean in object-oriented programming. They call this a method, I think. I mean, it's just a function. I don't know. So, and instead of, you write at the end dot and then the function, they call it a method. Okay, so this is here. And now the group by, you had it already in the previous video. That's very, very useful. That means it groups the data according to, for example, zip code. So then instead of having one data, you have 3 data sets, one for each zip code, and then it's indexed as each zip code. So you could do that yourself. You could, for example, create a dictionary with It will be just 2 lines of code, but I think this thing is optimized. So if you have big data sets, it will just be great to do a group by. And then, for example, here we'll have, you see, zip code. And for each one, I did the mean, the selling price, and then the mean. And I have for each zip code, the mean. And if I just do data group by, see here I do data group by zip code, selling price, mean, round. And so here now I store this information, and then I plot it here, and plot bar with matplotlib, and let's see if that works. Yeah, you could do it you could just, calculate, build a loop, and for each zip code quickly calculate. And but this one has, this group by thing has advantage. If you have a huge data set, I think it's faster than if you would do a loop. Don't know. So you see here enormous difference in price between the zip codes. Here I think we have the first plot, and we have this method that is for data. You can directly put dot plot, scatter, and it goes directly. Now here I made a little map for transforming each of the zip codes into a color, red, green, blue, and this is how the colors are encoded. And up here we go, we see the colors. You've already seen that. Now when you see this data, you immediately see these neighborhoods are totally different. The red one there is in Silicon Valley. Then you have two very different neighborhoods in Atlanta. There's no doubt that each one of them is pretty much on a line, so it makes sense to use a linear line regression line. There are these two outliers, and we'll see that probably there are mistakes, because you can see for this house in the past what was a past selling price, and was it back then also much higher than other comparable houses. And I checked, and I saw no, they are not, so I know they are probably just mistakes. So now we're going to work with linalg from NumPy, and here a list of data columns again. I don't know why. So here you have the formula for linear regression. Basically, for simple regression, you have a simple formula, but so you want to predict the selling price, expected selling price, given the information you have, for example, square feet, and you use a linear function a plus bx. Say square feet would be x. And why expected? Because two houses with the same features will have different prices. There's some randomness in there. So that's why the average price, if you had many houses with the same features, same square feet, same number, you could see what is their average price. That's this conditional expectation of the selling price given x. But the problem is we have quite a few houses, but very few which are exactly the same. Otherwise it would be a simpler problem. That's why we use linear regression to find out information for a house with a given square feet, for example. Even though we don't have other houses with those square feet, if it's a linear model, we can use the other houses of different square feet still to predict, because we only have these two parameters a and b, for example. Then we can use them all to predict a and b, and then use it for a house of which we don't have an equivalent one. And so you will see my video, intuitive regression. There's this formula, so you basically just have to solve this system of linear equations. So b are the coefficients of the regression. If it's a one-dimensional thing like here, b is a two-entry vector, a with a and b. It's a column vector. X is a data matrix. So if we have just a and b, we have a column with just ones and another column with the coefficients, say, of the square feet, and then X transpose is just a transpose matrix, and you have this simple system of linear equation to determine B. Y would be the column vector of the selling prices, and you see in my simple regression, this formula here, X transpose times X times B equals X transpose times Y, is given here. So I wrote capital B, but that's basically to solve for B this linear equation. And in this part here you have the ones, then we add the ones here to X, that is, we concatenate, that is, we make a matrix where you have X, but the first column of the matrix is made out of ones, and that's called concatenation. And we want Y to be a column matrix. So it's a little messy. Why did I put everything into NumPy, not matrix, but not array? It's for a complicated thing. Sometimes when there's just a column vector, then it says it's a series, and it messes things up. Whilst a column vector or a row vector are two type of matrices, and if you work with matrices, everything works. But sometimes with NumPy, when it's one dimensional, it says it's a series, and then it just doesn't work. I want, I just want a vector. For me, if it's a column vector, it's a matrix. If it's a row vector, it's a matrix with a dimension. If it's row 1 times n, if it's column n times 1, and everything works. But that's why I make here matrices instead of just arrays. So here we solve this. Again, X in this program basically is for one dimensional, but you could have X to be a matrix of data information where the columns are, each column corresponds to a feature. Y is the vector of the selling prices, and then the coefficient for the linear regression A and B are best estimated by minimizing least square, which I explained in my lecture notes, and which is just solving the system of linear equation. Here X times X transpose is a given matrix. X transpose times the selling price is given to us. So these are just numbers, and just B has to be determined. Anyhow, so by the way, quickly, I don't believe in using at first, when you learn this stuff, any pre-made regression or so on. Program everything by yourself. It's the only way to learn, because otherwise once it doesn't work, it's better to program, and later you can use the existing things which are optimized. But anyhow, as far as optimized is the thing which is optimized, Python is very slow. So why do we use it for data science? Well, because NumPy isn't slow. Under the hood, it's optimized and programmed, I don't know, in C or whatever it is. So I don't use Python. I use, for this calculation, NumPy, and that's optimized, so that's going to be fast. So then oftentimes if I use scikit-learn or so on, that's just a wrapper around the NumPy. It's not going to be much faster than what I have here, because the one thing which is optimized to run fast is under the hood, the NumPy. Anyhow, so here I run this cell. So then I will have the function simple regression, and now I'm going to predict the selling price using square feet. And you see here I have my regression line, and it's 1 second. So anyhow, so here we see regression wouldn't be too good. So now I'm going to here the set of the different zip codes, POM. So a zip code set is now the set of the different, now data Actually, here I kick out the outlier, because if you look here, the outlier is above 2 million. So here I say data selling price should be below 2 million, and the new data set is now cleaned. You see, I run this. Now if I run this again, this point is gone. Let's see. Yeah. And the other one was point number 15. So house number should not be exclamation point equal 15. So I cleaned up the two, and now I see already pretty good. Here we do for the zip code in zip code set, and so we run on the group by, zip. Uh, no, here I didn't use a zip code, the group by actually. Here I run a loop for each zip code in my zip code set. So here data zip code equals zip code. Here this is a data restricted to the zip code, and I run regressions, and I plot it here. A plus B00 is because B is kind of weird matrix something, and here I have the color which I had defined before, and so now you see I saved the figure, don't know where, but you see the relative errors are 18%, 23, 17. So this is median of the relative error, um, and yeah. So you see clearly these things are pretty much linear. There's almost no doubt to me. But clearly there are very different lines for each neighborhood. I mean, this one is much more expensive, and so on. So yeah, I already kicked out the outliers. Yeah, so that I already did. So here I did a little thing with the zestimate. So I compare the zestimate with the selling price, and I make the relative, because all this business of predicting house prices is based on relative error. So I compare it, and I see that they are at 7% error. So if we get down to about 10, 12, we're not that far from them. Again, let me just tell you, uh, this is not that important because uh, why? Because the reason is simple. Their estimate has already the information about the selling price which we're trying to predict. So to see how good they are, we should see how good they are predicting the house before it gets sold. That's a real thing. Okay. I also looked at time evolution, but we don't have really enough data, so uh, I can quickly show you this. Now I do a group by here. I run it on a group by. So let's quickly see if this works. Yeah, so here I have last sold date and last sold price, and that isn't linear. Recall one thing. It's still interesting to see. The prices collapsed when the crisis came, 2008. I don't have enough data points. I see the blue one collapse, and the green one, yeah, but you have maybe also not enough points, because here I have 3 points which are down, 3 points which are up. And in the red neighborhood, you don't see the collapse. So that's very strange, because even in Silicon Valley, there was a collapse of the housing prices. So I don't know why you don't see it in the red one. Is there not enough data? Anyhow, this is not going to be linear. It would be something which goes up and then down. But for this, you would need more data points, and yeah, the idea why I'm interested in this is, in principle, one thing you can see, if a house is really very exceptional, it sells above the predicted price in the past, that may be something useful for predicting its current selling price. That's the only thing. Okay, so here we programmed the multiple regression. Same thing as before, is based on this one equation here. And you can just, instead of x being a column, it's x is basically the matrix of the features, square feet, number of beds, and so on and so forth, whatever you want to put in it. So here, multiple regression, I don't add a column of ones, which would correspond to an intercept, because I think if I want it, I will add it to x before using this little function multiple regression. So let me run this. And now here, again, I work with a group by, so you have zip code, data. So for each zip code and each data in a group by zip, it will it shows you. And here I use for x the data, the square feet, the bath, and the beds. And here's the median relative errors, 23, 17, 11. Again, that's how in this business of predicting house prices, so the way they measure median of the relative absolute value of the relative error. Now, I'm going to try just to do square feet and square feet and bath. No, I'm not interested. Square feet and bed. And you see here 11, 13, 20. That's already pretty good. I said with 10 I'm going to be very happy. Now, bath, you see bath is not that good. 28, 34, and that's clear to me because bath doesn't predict so much. You can always add a bath to your house. It's not very expensive. So if you have $1 million home, adding a bath costs you maybe what, $5,000, not even, maybe 2,000, don't know. And so the difference shouldn't be what it costs to install an additional bath. So in the beginning, I already kind of assumed that bed is important, because if I have a big family, I want enough bedrooms, but bath I can add, shouldn't be so expensive. So let's see what this one does. I forgot. This is just based on beds alone. And I see that's much worse. So square feet is really useful. Bed is very useful. And you see here with square feet and bed as predictor. So in each neighborhood, I have each of these neighborhoods, obviously, I run the regression separately, because that's what this loop does, right? And here we have to do that because every neighborhood is so completely different. And I see the relative errors 20, 13, 11. That's quite good. Now, you could say, oh, maybe I'm overfitting. I would say probably not, because I tried only one or two things, and then because I just understand house prices is based on square feet and probably on the number of beds. That's common sense, and so they cannot be massive overfitting. But then you can do cross validation. But basically, as an experience, if you're experienced with data and you just check for one or two things, there shouldn't be massive overfitting in this. So 0-1 encoding, you have probably seen the video with the lectures and so on, how that is done. But here I want to show you for a small data like that, the problem is I may not have enough homes. I've seen that I have to differentiate between the neighborhoods. They're too different to use the same regression model. So I do a group by. This can also could be done using uh, interactions. I explain it in my other video. But here what you see, there are no ranches, duplex, bungalows in the neighborhood 30309 and 94043. Uh, but condo and townhome, and then condo and townhome is not in 30310. So if I would want to use all these things, it probably would be nonsense because they're not even present everywhere. So here I did what was that? I just want to see what's going on, and again, I restrict the data to the neighborhood considering, and now I'm going to run just for that neighborhood. I don't know what that is. I don't know, that must be a mistake. Here we go. We see what is available. And now I'm going to have a color map like before, but for the different type of houses. And now I run this, and oh shoot. Oh no. But anyhow, I'll have to reprogram this. But here you see most of these homes are single family, and then there are these few houses here which are not, but they are not really so much different if you make a line from the others. Hopefully it will run in the other thing. Okay, let's see if this one works. Oh, let's see what doesn't work. Yeah, I'll work on it another time, sorry. So after I had seen that, let's see if this one works. Let's try again. If it doesn't, it doesn't. Then I'll fix it. Oh. Don't know. I'll have to fix it. Oh. Okay, I'll fix that one of these days. Sorry. But then I see in this data set above, maybe single family is priced a little bit above. So I'm going to add a single family, because if I would differentiate between all the other houses, it will clearly lead to overfitting. So I see here one more time that single family is present in all of them, and then the other types are not present everywhere. But if you look at the data, single family is priced a little bit bigger. So I make a single family vector that's wherever the house type is single family, and that I'm going to use in all these neighborhoods. So now what I'm doing here is see, single family is where the house is single family. So here I subset the data to see if it has worked, and indeed here I've only the single family. So my single family vector is a Boolean vector which tells me where we have a single family home. Okay, let me clear this. It's sometimes good to clear a cell. I clear it because otherwise it becomes too messy. Now let's hope this thing works. what was that? So here, make this vector. Okay. So now I don't know what this is for. Let me see. Now here I run it just with square feet and beds, and now I'm going to run it but with single family. I've added before single family. You see here, this one, what it does, it adds me single family. Here is I make 1 times that Boolean vector. So if you look at it, let me quickly show you. Let's see what single family is. Single family. I'll run this thing. Sorry, spelling mistake. So you see, before it was a Boolean, now it's 0 and 1 vector. So I have this 0, 1 vector, and I'm going to, wherever a house is a single family, no matter what neighborhood, it's 1. When it's not a single family, it's 0. And I'm going to add this as a feature for my prediction. And how am I going to add this vector single family? Well, let me first clean up that. Clear. I'm going here. When I want to add to a data frame a column, I just do data. Then here I write whatever name I want for that column. I call it single family. And here is a vector of input which I want. In this case, it's my single family vector. So this line of data adds, and I'm going to show you, adds to my data frame an additional column called single family, and the input of this column is single family, is this 0, 1 vector, which tells me when I have a single family. To show you this, let me quickly show you another one. I'm going to insert a cell below. Now, data columns, here we go, and you see I have added single family, which was not in there before in that data frame. Okay, let me clean this out. Okay, and now we did a prediction here using only square feet and beds, and we got 20, 13, 11. And now I'm going to use single family as well, and I want to see if that really improves things. And I get 21, 17, 13. So no, it doesn't improve things. So at this stage, with that amount of data, it's certainly not worth considering the type of the house for prediction. Again, I want to tell you this is with a group by, so it's done in each neighborhood. So what we have is not single family, but a different single family in each zip code. You can also call this an interacting single family. So though we added at the original data single family, not differentiating between the zip codes, here it is differentiated because it runs a regression for each group, and each group is a zip code. In other words, it runs a regression for each zip code, and so it will use a single family coefficient different from each of the zip codes. So it's not worth adding. So the best we can do at this stage is probably stick to square feet and beds. And another question was, when you look at this, I was wondering if it would be worth adding an intercept, because we call our multiple regression, we run it without intercept. And it will just be interesting to see if for the neighborhood 3039, it would be worth adding an intercept. Again, that's after looking at the data that I came to the conclusion that that might be a good idea. So here intercept 3039 is a vector which is going to be 1 for 3039 and 0 otherwise, and then this way I have my regression here has an intercept in 3039. You see, if zip code is 3039, I add the intercept, otherwise I don't, because if I have a regression with one feature which is always 0, it creates problem. That's why I had to differentiate here. Now let's see. So I run this guy, you see now if I look at the columns, I have this intercept 3039. We can look at it, how it looks. Intercept 30309 false, true. It's just, yeah, it's anyhow. But then later here I added and put 1 times this, so it transforms a Boolean into a 0, 1. So now I have an additional, in my data frame, an additional column of 0 and 1s. I can show you data. Now I do data intercept. Here we go. You see it's the same as before, but instead of true or false, it has 0 and 1s. Let me clear the output here. Okay, and now I do my group by, and now we can see again. Why did I add an intercept in 3039? I saw the data, saw the picture, and it seemed pretty clear that in that neighborhood that regression line didn't go through 0. Now oftentimes in selling price prediction you have straight lines going through 0, because a house with size 0 should be worth 0, but not always. So let's run this. Oh, you see here we have decreased quite a bit, so I'm pretty happy. I would leave that. Is that now significant? You could do a test and, you know, to see if you have significant evidence that it's worth adding that intercept. But again, from just looking at the plot, it seemed to me. So I'm pretty happy. 18%, 13, 11. And then the L1 regression I will explain in the next video. It's not fully working yet because we will have to use gradient descent, but yeah, that will explain in the next video. Thank you for your attention, and yeah, it was great to talk to you. Bye bye. Bye.